Okay, so welcome to lecture 11. Um, we'll continue with analysis of Lipschitz continuity and smoothness of machine learning objectives and move on to algorithm for optimization, where we'll realize the importance of Lipschitz continuity and smoothness in addition to convexity when it comes to analysis. Um, so this outline, uh, we will conclude our discussion on the homework problems. And then you can actually look at my detailed convex optimization course where I have more illustrations for Lipschitz continuous functions and gradients. But however, we will move on to gradient descent and analysis for Lipschitz continuous smooth and strongly convex functions. I won't be doing all the analysis and details at all points of time, so I'll do some of them in details and then leave the rest for you to read up because they follow very similar patterns, right? And the two most important, tricks I would say are kind of converting dot products into quadratic equations, quadratic forms, and the other is telescopic summing. Okay, so what we'll do is illustrate the key um, tools, right? Okay, so there is a key tools for such analysis include, as I said, algebraic manipulation. For example, dot products converted into quadratic forms. And the second, another set of tools is telescopic summing. There's sum across several indices and several terms get cancelled in that process. We'll also look at rates. Again, that's going to be extra reading, extra optional material on rates and orders convergence. So okay, but we want to apply this uh, for gradient descent, try and prove that, and then also show what the effect is for several other algorithms. I mean, I've just put a dot here next to accelerated gradient descent, this conjugate gradient descent, and proximal gradient descent, and so on. Yeah. So let's recap what we discussed on Lipschitz continuity. Lipschitz continuity limits how fast a function changes, and the critical part here is that you can link this very easily to the subgradient. So recall that this entire expression um, can be intuitively restated as saying that the rate of change of the function, that means I'm now dividing by the distance between x and y, norm of the distance between x and y, and this will be upper bounded by L. And we saw that if F1 and F2 are Lipschitz continuous, then the sum is Lipschitz continuous, product is Lipschitz continuous. In fact, we can also show that composition is Lipschitz continuous. And that's something we might require today in case you have done your homework. Um, so if composition of Lipschitz continuous functions is Lipschitz continuous. Do you prove this? You might have required this today for your homework. Fairly simple proof. So let's say F1 and F2 are Lipschitz continuous. Their composition is also Lipschitz continuous. How do you prove this? So if you have F1, let's say F1 is Lipschitz continuous with L1, F2 is Lipschitz continuous with L2, right? Then you have F1 of F2 of, what will you look at? Say something like X and Y applied in the sense of the composition. sorry. Okay, so there are absolute value difference of the absolute value. Now you realize that f1, sorry, f2x and f2y are just two evaluations, right? So this will be less than equal to the Lipschitz constant L1 for f1 times the absolute value of f2x minus f2y, the absolute value of the difference, which you know is less than equal to L1 times L2. So Lipschitz constant for the composition is the product. Simple. Okay. I'm assuming you would have required this in your homework. Okay, so let me copy this. You might require this when I talk about the homework. Then we also talked about Lipschitz smooth functions. It was a rate of change of the gradient of the function. And yeah, let me recap that this again had an interesting connection with strong convexity. Recap that in the case of strong convexity, we had a quadratic um, yeah, we basically had a quadratic lower bound. Basically, function cannot be flatter, right, than something. Whereas here we had a, no, a quadratic upper bound. Okay, so this is discussed again. I'm not going to recap, but yeah, this was the idea here. Function cannot be too flat, and now we have come up with an analog of that. Okay, and then we also discussed Lipschitz continuity and smoothness, strong convexity. The connections are very important result which I just stated, which I'm not going to prove, but which is somewhat intuitive. Is all of us feel that okay, Lipschitz smoothness seems to be more strong. I mean, a stronger condition than Lipschitz continuity, and it turns out that it is if your function is bounded. I'm sorry, if the function is over a bounded set. So the set on which you're evaluating the function must be bounded. So in that, yeah. Now this is not um, a necessary condition, is a sufficient condition. If the function is over a bounded subset of Rn, then typically when you say that f is smooth, then you would imply that f is Lipschitz continuous. Okay. Further, the subset is not only bounded, if it's also closed, then you know, if basically f is convex, then you would have that it's Lipschitz continuous. So most convex functions are well behaved in many ways, including Lipschitz continuity, not just continuity. Okay, so this is again a result we stated, and I left you with lots of some nice reading on Lipschitz continuity. Now I'm going to draw your attention to the last two references which I had also left in the last class. Um, these are examples of papers that attempt to compute the local Lipschitz constant of various deep neural networks. Now, it's the local Lipschitz constant because there could be local convexity. Local properties is what we typically analyze. Okay, so mark this keyword local, but that is important. That helps you analyze convergence. So there are some papers, I've put the links here. You can pick these up for seminar reading, by the way. So I'm adding to the list of seminar papers. This is uh, um, added to the list of seminar papers. In case I've forgotten to add, do let me know. You're also free to suggest more papers. Okay. Yeah. So go back to the homework problems. Let's take the first one, which is logistic loss. What's the idea? How would you prove that logistic loss is Lipschitz smooth? Anyone? As I already gave a hint, you could think of composition, right? And hopefully you've tried using composition. So could you divide it into two parts? Part one, where you take a simple function f1. Okay. So let's say proof sketch using composition. Oh, by the way, this is I did this for Lipschitz continuity, but you can probably do it for Lipschitz smoothness as well. Okay, I'll not get into that right now, but yeah. So Lipschitz smoothness based on composition. So the part one, what would I do? I take this f1, let's say t, which is log of 1 plus e raised to t. Okay, that entire numerator, that exponent is t. This is f1 t. And what would I do? I look at f1 dash t, which is e raised to t divided by 1 plus e raised to t. And f1 double dash t, because you're looking at Lipschitz smoothness, you may want to just see if the double derivative, the Hessian, is upper bounded. Okay, so is that? So you'd use the quotient rule. Rule of derivative. Yes, anyone has derived this? Please let me know if you have attempted and you have a different way of solving it. That's also welcome. So if I have d by dt of a t by bt, what's the derivative? It's a dash t, b dash t, sorry, bt minus b dash t at, the whole divided by t square. So using this, what do you get as the derivative, the double derivative? You can derive it. It's it'll have e raised to t, 1 plus e raised to t in the numerator minus e raised to t times e raised to t, again the numerator, divided by bt square, which is 1 plus e raised to t square. And this is nothing but all this e raised to t and e raised to t square will get that will get cancelled out. Only e raised to t will remain. So e raised to t divided by 1 plus e raised to t the whole square. What is this? Is this upper bounded by some constant? Yes.
It's at most half.
It almost half. In fact, you can liberally take it to
Sorry,
be one.
not half. 1/4.
One over
4.
4. Yeah, I mean, you can come up with tight bounds. right? So half is a reasonable bound. Yeah, you can also take it to be 1/4. Yeah, check it out yourself. So basically it's Lipschitz smooth. Okay. So this function is, and now let's look at another function, f2t. Uh, Actually, let's have it as x. Oh, this theta, f2 theta. What is f2 theta here? I mean, the summation is actually not a big deal, right? Summation of f1s. This is okay. So f2 theta is simply minus yi theta transpose xi, right? And this is Lipschitz continuous, Lipschitz smooth. It's upper bounded, right? It's upper bounded by a quadratic term. In fact, the double derivative if you take, you'll just get 0. When I say it's upper bounded by a quadratic term, the difference of the gradients. Um, so basically, the Hessian upper bounded by an L which is equal to 0. Okay, so basically now you can prove. Let me just use a different color for this. So then what you have to do is just do a summation. So summation over i's. So I is not a variable as such. I mean, I is indices into different x's which are fixed, right? So this is nothing but f1 of f2 theta for different values of i's and y's. Would therefore be Lipschitz smooth. Is it also convex? Yeah, it's also convex, right? We have done that. That we have. So convexity will just come from our previous discussion. I'm not bothered to show that again here. Okay. Next one. Lipschitz continuous. Hinge loss. Any suggestions? I'll do couple maybe little detail. Others after a point you will pick up yourself, right? Hinge loss. What would you do? Again, my suggestion is use a simpler function. What would be a simpler function? Any suggestions? Use composition wherever possible. So you could take a max of 0 comma. This entire thing I'm going to abstract as t, like I did earlier, right? 0 comma 1 minus t. That's my f1t. So now I'll have to look at the difference, absolute value of the difference between the function values. Say t1 and at t1 and t2. So I'll consider cases. What are the cases? Yeah, anyone? What cases will I consider?
1 minus t negative or 1 minus t positive? Because you're taking with the 0, I guess.
Right. So 1 minus t negative or positive. But no, now look at the, okay, let's write down, right? So case 1. I'll have to consider the case where absolute value is f1t, right? f1t1. I'll just drop the 1 in this index here. It's just getting too, there'll be too many ones and twos. So this is just ft, and we can do a composition later on. So f of t1 minus f of t2 is absolute value. What is this? So this is, so now you'll have to consider cases, okay? Is max of 0 comma 1 minus t1 minus max of 0 comma 1 minus t2. Okay, so I'm going to just consider cases. So case 1 would be t1 less than 1. See, if t1 is less than 1, then immediately the second part peaks, right? And if t2 is, let's say, greater than or equal to 1, then the first part peaks. All right, or you can consider the other case where t1 is greater than or equal to 1 and t1 is less than 1. So in both cases, I mean, you'll have only one of them surviving. Okay, let's take the first case. I mean, case 1a, call this A if you want. Let's consider this case. This case, what will happen is you'll have 1 minus t1 emerging as the max here, minus 0 emerging as a max for t2. Sorry, this is t2. Okay, so this is 1 minus t1 absolute value, right? And this is what? I mean, how is it related to t2? Always less than or equal to. So see, t2 is greater than or equal to the 1 in the first case, right? So it is less than or equal to t2 minus t1. And naturally L is equal to 1. I mean, at least there's one L which you have showed. Okay, so this is a yellow case. They can likewise do for the second part, right? So I'll kind of leave it to you to do the second part. Okay, so this is case 1. Let's look at case 2. What would be case 2? You'll have both of them less than 1. T1 less than 1 and T2 less than 1. Then what would happen? Yes. What would this be? In both cases, you'll have 1 minus t1 and 1 minus t2 as a max. So this is less than, I mean, this is exactly equal to 1 minus t1 minus 1 minus t2. Is even more straightforward, right? This is basically just t2 minus t1 absolute value, which is less than or equal to t2 minus 1 sorry, t1 absolute value, amounting to again L equals 1. Did someone have a question? Okay, so let's just do the third case, which is I would say the simplest of the lot. Right, so the case 3, both are greater than equal to 1. Okay, so this case you're just dealing with 0 minus 0, which is always less than equal to the absolute value of t2 minus t1. Yeah, I mean L can be 1. I mean you can take L less than 1 is also fine, less than equal to 1. Okay, we are done with this, and then you can do a composition. Right now, um, subsequently you can just consider the composition of f of the linear this function f is a linear function, like in the previous slide. With a linear function exactly as in the previous case. So this is very simple, as we have seen. Yeah, I mean there can be more complex settings, but I think our first principles are often very helpful. Now, multi-class logistic regression, I won't do this, but simply a generalization of the logistic case. Okay, so I don't see any challenge extending that. Therefore, we'll move on. Least squares. Any suggestions? So, by the way, all the previous were convex. Huh? I'm not stating them again and again. We have already done their convexity. Okay, just while the first they are also convex, now we have come up with a case, the least squares, which is strongly convex and it's also Lipschitz smooth. Okay, and this again is very straightforward, right? I mean, we have done the simple example of say ft equals t square, right? So recap that this is we have done this is both Lipschitz smooth and strongly convex. And again, we are dealing with a composition. Now, is it also Lipschitz continuous? By the way, is logistic loss? I forgot to ask. Is logistic loss Lipschitz continuous? In general, Lipschitz smoothness need not imply Lipschitz continuity. But in many cases, as we have seen, right, and bounded regions of the Rn, you typically have that Lipschitz smoothness implies Lipschitz continuity. And more so for logistic loss, it turns out that it's also Lipschitz continuous. So I should probably have mentioned that there. Okay, so this can also be okay, I mean I'm assuming you will probably try this out. Okay, so this turns out to be Lipschitz continuous as well. How about the next one? Hinge loss. It's already Lipschitz continuous. Smoothness is going to be very difficult. Okay, smoothness. I mean, see, the smoothness requires something over and above just, you know, the gradient to be there on, infinitely many points. Basically, it's not differentiable at a um, some number of points almost everywhere, right? But smoothness requires little more than that. So we can't say this will not be Lipschitz smooth as far as I know. But what now we are coming to is least squares, which is both Lipschitz smooth and strongly convex.
Sir, one doubt before that.
Yeah,
So when we say Lipschitz smooth function, so like they are allowed to be non-differentiable at like only countable number of points, or can the number of points be countably infinite?
yeah. So if you recap our overall positioning, Lipschitz. So the definition of smoothness didn't talk about differentiable almost everywhere, but it turns out that f is smooth is the same as saying that it's different. The gradient f is differentiable almost everywhere, right? But unfortunately, with L1 loss, hinge loss, we can't say that either, right? I mean, you can say that f is differentiable almost everywhere if it's hinge loss. We saw that concentric circles last time, right? So hinge loss is or L1 loss is differentiable almost everywhere. But now we want the gradient to be differentiable almost everywhere, which is not easy. Yeah. So does that help?
Yes, sir.
So we would not expect the hinge loss or L1 to be smooth. Okay, so this let me make this point. Won't expect smoothness. Uh, Basically amounts to differentiability. Its gradient almost everywhere. So case for both hinge loss and L1 loss, L1 regularization. So good that there are some very pertinent questions, I would say, because you deal with these losses, right? So we are not dealing with just general optimization problems. We are dealing with machine learning optimization problems. So nice questions. Okay. Okay. So least squares is Lipschitz smooth and strongly convex. In a bounded region, I would also expect it to be Lipschitz continuous, right? Because it implies, right? So in a bounded domain, also expect least squares be continuous, which means an upper bound on the rate of change of the function. Here we already know that there's an upper bound on the rate of change of the gradient. So otherwise, never assume that one implies the other. Now we start looking at combinations. L2 regularization. Before we look at combination, we look at regularization. Okay. L2 regularization. Now by similar argument, right? It's very similar case to what we saw. F of t square. Now this t can be applied to a vector x, and that's what happens in L2 regularization. So here, let's say this is nothing but f of a linear transformation, right? The previous example, but now I have applied it to norm of x, to norm of x. Okay, so the same. I mean, the overall idea is that same argument. We have the same argument. Any questions on this? If not, let's look at one last case, which is L1. Again, I would say L1 regular reasoning is going to be very similar to hinge loss. Okay, so this is similarly. It's going, both are convex. So that goes without saying. They're both Lipschitz continuous. Any questions? The reasoning is slightly different. Okay, so I mean, reasoning is similar but not the same. So I would say, if you want to be safe, just let's avoid doing this. Let's let's just go back to the first principles. So recap. We showed that the one norm of x is Lipschitz continuous. In fact, this is simpler than even the Hinge loss. Hinge loss, we had to at least consider some cases. So this should be a better way of stating it. Now let's look at combinations. So L1 regularized logistic loss. So it turns out that sum of Lipschitz continuous or Lipschitz smooth functions is Lipschitz continuous or Lipschitz smooth respectively. So logistic loss is Lipschitz continuous. L1 is Lipschitz continuous. Therefore, the sum is Lipschitz continuous. So recap. Sum of Lipschitz continuous functions. Okay, so that is not an issue. Convexity also, because sum of, so I think the same sum of Lipschitz continuous. The same thing I'll say. Sum of convex functions. Same argument. Okay, so this should be a possibility. I mean, this should be an easy proof. How about L2 regularized logistic loss? Now, sum of Lipschitz smooth functions, is it Lipschitz smooth? It turns out that same logic holds, right? Sum of Lipschitz smooth and Lipschitz continuous functions are both Lipschitz smooth or Lipschitz continuous respectively. And however, for strong convexity, you don't need both to be strongly convex. So sum of convex function with the strongly convex function still strongly convex. Okay, so just make a note here. Okay, so this strong convexity is largely because L1 sorry, L2 regularizer strongly convex. Sum of convex plus strongly convex function is strongly convex. On the other hand, Lipschitz smoothness is can be attributed to the fact that we are dealing with the sum of two Lipschitz smooth functions. Okay. So many of these are just following the the definitions or some of the simple properties we showed in the last class. By the way, sorry. The third one, L1 regularized hinge loss. It's Lipschitz continuous. Why? Anyone wants to give a reason? L1 is Lipschitz continuous. Hinge loss is Lipschitz continuous. So it's again same sum. I mean, in fact, these things are become easier now. There's some property or some calculus, and this is the sum property of both Lipschitz continuity and convexity. Finally, L2 regularized hinge loss is because hinge loss is convex, right? So that's important. Hinge loss is convex, whereas L2 regularization brings you strong convexity. Now it's Lipschitz continuous. Okay, that's important. On bounded set, L2 regularization will also be Lipschitz continuous. There's always Lipschitz smooth, but on a bounded set, we know that Lipschitz smoothness implies. Okay, I'm not going to keep saying Lipschitz. There's a abbreviation. L smoothness implies L continuity. Okay, we'll use L hereafter on a bounded set. That is. L2 regularized least squares. Now this is Lipschitz smooth. Why? Because both the components have a quadratic form. This is one of the rare ones which has both properties. Lipschitz smoothness and strong convexity. And in general, Lipschitz continuity doesn't go well with strong convexity. That's another point I want to make. Okay. So these, the previous slide, what I showed, these generally don't go together unless you have a bounded set. Okay, so this is important to point out. Generally, they go together only on a bounded set. How about L2 regularized least squares? Yeah, we have seen that both components have a quadratic form. This is simple. I'm spending a little more time here. This is critical. This is all ML, and this is going to be very handy for you. Okay. Are we done? There was one more, right? And again, Lipschitz continuity and strong convexity. Just like this is an interesting case. What has happened is you had some property. So let's say this property, L2 regularization. Now, L2 regularization gave you strong convexity and Lipschitz continuity on a bounded set. Okay, so on a bounded set, it gave you Lipschitz continuity. That property was also satisfied by least squares. Okay, so on a bounded set, again, this on a bounded set is very closely connected to the fact that we are dealing with Lipschitz continuity. And what has changed between these two is that hinge loss has now taken the place of L1 regularization or vice versa. So these two are analogs. L1 regularization and hinge loss are analogous. L2 regularization, least squares are analogous. As both L1 regularization and hinge loss, both of them are Lipschitz continuous. They're just convex. They're not strongly convex. Okay, so the strongness has actually come from this part, L2 regularization or least squares respectively. Okay. So one question might be, okay, what about neural networks? Again, I'm going back to my references. All these analysis um, hold for the last layer, right? All these analysis hold for the last layer of neural networks. They are often analyzed locally. Okay, this is going to be important. They are analyzed locally, and that's where I draw your attention again to a reference that I had given today, and also in the last class. I'm just going to draw your attention to that particular paper, those two papers. One is Neurips and Neurips 2020, but there'll be more, probably more recent ones which you can find out. Okay. So yeah, so they are often analyzed locally. That's important. Any questions? Otherwise, we'll move on to the next important part, which is algorithms. Any questions? We are now moving to the next part of our um, course, which is algorithms. You have all the ammunition now required to move to algorithms. Okay, so algorithms for optimization. As you might imagine, the key idea in any algorithm is that you're basically moving from one point in the space to another point, and the best way of studying these is through the notion of level sets. Okay, so we are going to often bring this up, the notion of level sets. Let me just paste an image here. We'll be often using this. So you have level sets, and what is happening is the function could move from this green point to another level set. It could also jump from what you see, this gray point here, to another gray point, which unfortunately is in the same level set. So what's happening is you're dealing with two important components in the algorithm. One is the direction. The green and gray have different direction. In the levels space view, and the green and the gray also have different magnitudes. Okay, so gray one, for example, larger magnitude. So this is a larger magnitude step, the gray one. The green one is a smaller magnitude step, but also they have different directions. Okay, so uh, in the level space view, we'll be often dealing with these two, the magnitude and the direction. These are two key components of any algorithm. Now, where Lipschitz continuity strong convexity have start playing a role is that for the choice of direction and the magnitude that you have, well, how fast will it converge to the optimal solution? So imagine that the optimal solution was lying right at the center here. Okay, so let's say this was a center, the optimal point. You want to arrive this quickly, right? So if you take the gray step, you oscillate. I mean, you might be oscillating the way you have taken very large steps. So you want to take small steps and the right direction. So convergence, to show convergence of any algorithm, we would make use of how fast the function changes, right? That's Lipschitz continuity. To show or analyze convergence modulo magnitude and direction, we would like to assess what, for example, how fast the function changes. That's Lipschitz continuity. Often we'll be dealing with gradient based steps, in which case we also look at how fast what is the curvature. So if it's curved upwards, it's convex. If it's curved sufficiently upwards, it's strongly convex, right? But if the upward curvature is upper bounded by some value, then it is Lipschitz smooth, right? Upper bounded, lower bounded. Because if the function is too drastically changing, then you have a problem. For very drastically changing functions, which means that I'll basically if the function is that's actually related to continuity, but I make function change oscillates, right? Oscillates could be because of drastic changes. Then oscillations can happen. The updates based on magnitude and direction, it also lead to oscillations or oscillating solutions. And of course, convexity becomes important when you talk of existence of a global minimum. Then you can talk about convergence to that global minimum. So these are some of the considerations. If you have questions, let me know. These are, I would say, highly important meta level questions as we plunge into algorithms. Any questions? So the most popular algorithm which all of us are familiar with is the gradient descent algorithm, right? And what's the idea? Given a convex function, if you want to go sufficiently close to the optimal solution x star. So we know that for a convex function, we expect x star to exist. I know we have done the Weierstrass theorem, as per which there are some conditions under which there will be a global minimum and so on. So notwithstanding that, we will revisit those theorems whenever we require. But let's assume that there's an x star, and that's where convexity becomes handy. It might be a local minimum, I mean, in which case we are talking about local regions of convexity and so on. And just to mind the notation very carefully, so x star will typically refer to the argmin. Okay, argmin is the x that minimizes fx. Okay, this is the whole idea. Iterative algorithm, initialize x naught either randomly or say to 0, then set your next iterate xt plus 1 to xt minus some gamma times the gradient. So this is a gradient descent algorithm. Gradient descent belongs to a general class of algorithms called the descent algorithms. So this this gradient could be replaced with any descent step. So general descent algorithms is the gradient with some descent step. Okay. But nevertheless, this is a descent. This is more important for direction than magnitude. Okay, that's important. Uh, this component for the direction component. We have now separated out the magnitude discussion into the gamma. So the gamma is taken care of all the magnitude part. Okay, so it'll be nice to always keep the picture, the image from here in mind. We'll keep this in mind. Okay, so I just bring this back here. This gamma is a step size parameter which needs to be set, right? For example, if at this point, this larger magnitude step. So at this point, setting gamma to be large is a little dangerous also. I mean, you can set gamma to be large at the green point. Okay, can be dangerous at a large value of gamma here, right? Whereas that at the green point, it is not the case. This is dangerous here, but here you can probably play a little bit with gamma. The reason we are this direction is not good is because it's moving away from the point of minimum. It's not good. It's not. It doesn't seem to be arriving at that black point, at the gray point, right? At the gray iterate. Okay, so this our comment here is, yeah, can risk a slightly larger value of gamma here. Okay. Any questions? So we want to be able to, of course, estimate when to have that large value of gamma, when to have the small value of gamma. Then, in fact, there are algorithms for determining the step size itself. There's all and the conditions, Armio conditions, Frank-Wolf conditions, backtracking search, and so on. Yeah. Now, another important point I want to say is gradient is some descent step. But the other interesting thing is gradient is orthogonal to the level served in the direction of maximum degrees. So that's another point you note. I mean, that's especially evident in the green point here, the green um, iterate here. Okay, so this is another point. Gradient points in the direction or orthogonal to the levels curve at that iterate slash point. Okay, I mean that doesn't mean that you can take a very large step. This is not a license for becoming very large, because as you see in the case of the gray point, it probably is orthogonal even here. It's orthogonal, right? But here it hurts. See, if you are dealing with concentric circles instead of ellipsoids, you probably are safe. You can take large steps because all the gradients will point towards the center. But that's not case if you're dealing with ellipsoids as against circles. Okay. So now the critical question is how much time does it take to reach an epsilon approximate solution, right? I mean, when I say epsilon approximate, I'm asking questions such as, you know, the time. Can I now characterize this as a function of the epsilon? What functions can you think of? Is it 1 by epsilon? Is it 1 by epsilon square? Now is it log of 1 by epsilon? Which of these three will be most preferred? Question for you. Please answer. Yes, I'm awaiting your answer. Is it 1 or 2 or 3? Hello? Yeah, I'm awaiting your answer. Hope I'm audible.
We'll prefer the third one, right?
We'd prefer the third one. It's taking less time, right? So log of, I mean, you don't want 1 by epsilon square. So smaller the epsilon, larger will be 1 upon epsilon square compared to say 1 upon epsilon. But 1 upon epsilon still is becoming, it's shrinking slower than log of 1 by epsilon. Okay. I mean, so 3 is the most preferred, followed by 1, followed by 2. Okay, so if I want to get x star, which is the global minimizer of f, I want to get it in the smallest amount of time. So now we back to we'll start with analysis, and we are back to Lipschitz continuity. Lipschitz continuity, as I said, is a little bit more general. At least on functions on bounded sets, it's general. So we will start with Lipschitz continuity. We'll also invoke convexity at some point of time. All these could be, as I said, a local. So we invoke L continuity. In practice, it is more generic, especially on bounded sets. Okay, so it's weaker in some sense, and you will find that this actually leads to weaker time guarantees. Okay, that's very interesting. You will get it um, verified. Interesting. This apparently weaker condition to weaker time guarantees. So if f is smooth, so that's what we'll begin with. But if we also have cases where we'll look at the tighter case, the more stricter case. Then you'll have a parameter L. So I'm just bringing up front what are the different parameterizations that might come up. L typically would mean smoothness parameter. Okay. And this turns out to give you better guarantees. Yields better time guarantees. And in fact, I'll be illustrating all of these through a note. I'll be sharing with you a notebook, which I'll be illustrating these different algorithms. So hopefully you'll get a better idea. We'll be doing that in the next class. I'll share that notebook beforehand. Okay, this is the idea. Gradient descent. You're trying to move um, orthogonal to the level curve, but you want to be informed. Now see, this x1 has become x2, very large step size. Then x3, x4, x5. Now you can see the step sizes are shrinking. Okay, so step size also has an important role to play, as you can see. Now what is that step size? Right, so there was some gamma here, some other gamma there. So uniform step size doesn't seem to be a good idea always, anyways. So let's say this is gamma 1, this is gamma 2, and so on. Under what condition does it converge? So we'll begin with some simple analysis. We'll refer to GT as the gradient of f at xt, and from the definition of gradient descent. So I'm going to apply some analysis now. Um, it'll be nice if you have some pen and paper ready. Okay, so we already saw the gradient descent step. Okay, so recall the gradient descent step. Xt plus 1 is xt minus gamma times gradient f xt. Now I'm just writing the same thing differently. So okay, so sorry, right. So what have I done? I've just added this x star on both places. Okay, so xt minus x star, and then I have also introduced a dot product. Okay, so it'll be useful to see how did we arrive at this um, expression. Yes, I would like you to suggest how we have got this expression. How exactly are we here at this point? What transformations will lead to this expression? Anyone? What would be your transformations? Yeah, please do prompt, right? Xt plus 1. So how do I get x star here?
Like we could take x this gamma times gt on the other side and bring xt plus 1 to the right side.
Right. So this just
Then
gives you an
divide
expression.
by
Correct. So gt is 1 upon gamma xt plus. Yeah, I just want to make sure all of you are attentive and awake. This is a very simple transformation. Gt is 1 upon gamma xt minus 1 xt plus 1 minus xt. That's all. We've just plugged that in here.
now transpose both sides and multiply by.
Transpose both sides and multiply by xt minus x star. That's simple. Okay. So this part is the same. So we'll get familiar with some such algebraic manipulation, which become quite key to derivation. So now what we'll do is we'll give these names. Okay. So um, the reason we'll give these names is because we want to move from dot product to quadratic expressions. Remember, one of the tricks we're going to keep invoking is going from dot product to quadratic expressions. This is all algebraic transformation. quadratic squared expressions. Okay, so toward that, what I'm going to do is give this names, give these names. Okay, so I'm going to call this, say, this expression as a W and this expression as a V. Okay, and then I can write down 2V transpose W. This is V transpose W, but 2V transpose W. What is the relation between that and norm squares or their differences? Anyone? Can I write this as something as norm V square plus a norm W square and something in terms of the norm of V and W? Now norm of V minus W or V plus W?
Minus the norm of V minus W square.
Minus the norm of V minus W square. This is it, right? Okay, so this will give a transformation for the left hand side. And we'll see what happens to the RHS. Okay, RHS has only W, it doesn't have G transpose, I mean, directly. Okay, so this is the first step, 2V transpose W. Again, I remind you, this is V, this is W. Okay, with this expansion, we'll also do something to get the RHS into shape. Our goal here is that the RHS be such that you are able to do this telescopic summing. Remember, I talked about the second algebraic trick. Transform, we will want to transform the RHS so that we can have a summation. Okay. And the specific goal is to have, say, xt minus x star, xt plus 1 minus x star of differences. That's exactly what you see here. Summation of differences across from the x star across iterates. Okay, so let me just highlight this part. This part is what I'm talking about. I mean, we have done something very similar here. We have again done squared expressions and all that, right? So what we have done is xt. I mean, we have done the same thing: xt minus xt plus 1 square plus xt minus x star square minus xt plus 1 minus x star square. That's the right hand side. What happens is that yeah, you can do the same thing here. So if you want, you can again have a v dash, v prime, and a v dash and w dash here. Use the exact inequality, this exact equality here. Okay. And when you subtract xt minus xt plus 1, from that you subtract xt minus x star, you basically land up getting xt plus 1 minus x star. This is the expression you get. V minus w square is xt plus 1 minus x star square. Okay, so now what have we got? So these are the two terms I'm drawing your attention to. One is xt minus xt plus 1 minus of xt plus 1 minus xt square, x star square. Okay, this expression. I'm sorry, xt minus x star square minus xt plus 1 minus x star square. Okay, these are the exact two expressions we have. And what happens is, if I now sum this across different values of x star and xt around across different values of t what would happen? What would happen when I do a summation? By doing that, and I'm also waiting for your prompt. Okay, so if I take the, let's say the left hand side, right, and I do a summation across iterates, t equals small when 1 to say t minus 1 of left hand side, what happens?
Uh, at least for the highlighted part, we'll only have two terms remaining, the initial time and the final time.
Right. So let's write that down. So gt. So now xt minus x star, we'll have to do a summation across all values of t. Nothing will get cancelled on the left hand side, right? So this is the left hand side. Nothing vanishes there. But yes, on the right hand side, we will have some simplification. The simplification will be in terms of this part, as you said. Now xt minus xt plus 1, I have already simplified to norm gt square. So let me write that as usual. So this is summation gamma by 2 t equals 1 to capital T minus 1 norm gt square plus, exactly as we pointed out, only two terms will remain. The terms corresponding to z whatever 1 t1, because you'll have t1 minus x star square minus xt2 minus x star square plus xt2 minus x star square minus xt3 minus x star square. Okay, I hope you see that happening. I will write that down, but yeah, you'll have x1 minus x x star square minus norm x2 minus x star square plus from the next value of t, you'll have x2 minus x star square plus x3, I'm sorry, minus norm of x3 minus x star square, and this will go on. So the next term will obviously be x3 minus blah blah blah. Okay, so what will happen is obviously these alternating terms will get cancelled out. Get cancelled out. These two will get cancelled out, and what will remain as the first and the last term? The last term would be what? What would be the last term? Which would remain, which should not get cancelled out, will be a minus of norm of summing till capital T minus 1. So you'll have a xt x capital T minus x star square. Okay. Okay, so only the first and the last term will remain. Of course, there'll be a 1 by 2 gamma. So overall, you have 1 upon 2 gamma x1 minus x star square minus of xt minus x star square. Okay. Now, so this such telescopic summing. This is exactly what we have been referring as telescopic summing or illustration of telescopic, which should actually excite us, and we should look for such telescopic summing. Okay, so now how do we take this forward from here? One thing to notice, we are looking at difference between x star. We might, in some cases, we will be able to write difference between f of x star. Okay, so I would say that's like a little bit more thought process for the future. Um, Let me write a for the future. Can we seek such telescopic summations on differences of function values rather than points? See, the problem with points is that after all, uh, 2 points might be very far away. Still, their function values may be very close, or 2 points may be very close, but their function values may be large. Why can't we directly do this on the function values? Okay, so this is just a question, a food for thought. Let me call it a food for thought. Okay, but for the time being, let's stay with what we have. We want to now take this to some conclusion. Any suggestions? What do you do with norm GT square? Could you make use of Lipschitz continuity?
Uh,
I want to
we
do
could
something over the.
like we can upper bound it.
Okay. We can upper bound this term, right? The norm GT square. Good point. Yeah. Okay, so let's move on to the next slide. So we are summing over all iterations. Okay. We have the second expression. Norm, sorry, gamma by 2 sum of norm GT squares. The left hand side is what we had in the previous expression. So the next step we are saying, okay, can this be upper bounded based on what? Lipschitz smoothness, Lipschitz continuity. Continuity.
Yes, continue.
Okay. And it turns out that yes, that you can. I mean, as I said, that's going to be the simplest assumption we make. Okay. Um, yeah. Why is this called 7? I think there's some typo here. Yeah, this is basically 1. And I'm really referring to this part. This part gets kind of cancelled out, or what survives is only this part. Okay. Now, as I said, now we are trying to address the part in orange. So Lipschitz continuity is one point. Is there something else also we should be doing? We also need to do something with the left hand side. What do you do with this part? What is a property we have not used so far? Right? So almost by elimination you can figure out, there's some property we have not used so far. What property have we not used so far? Convexity. Can we use convexity here? So can we do something with this term? Say upper bounded. Why are we talking about upper bounding everything? Maybe some of them we may want lower bound, but bounded. So let me just make it more bounded based on convexity. Well, we will talk about upper bounded. because we want to upper bound the number of epochs, okay, number of iterations. So upper bounded. And this be upper bounded based on convexity. What is this basically? This term is a linear interpolation, right, between 2 points. Linear approximation, and we saw that this is a lower bound to the actual function values. So let's start with the, I mean, there's the green part and the orange part, both need to be addressed. But let's start with the green part. So we're going to invoke convexity with x equals xt and y is equal to x star. Okay, that's the green part. And all of you know, I mean, by now we have seen enough, but nevertheless, I'm going to basically let's just write down this. Okay, you can see this image. F of xt, f of x star, and then there is this lower bound function. Okay, and that same thing has been rewritten. Okay, f of xt minus f of x star is less than or equal to gt transpose xt minus x star. But we were trying to get the green part, right? So this has been rewritten here. Okay, so now the gt transpose xt minus x star is upper bounding the, is yeah, upper bounding the f of xt minus f of x star. Okay, actually I should be using lower bounded. Yeah, this is lower bounded. We'll be lower bounding this, but let's just proceed one at a time. I've given hints here, but let's see how it pans out, right? Okay, so now I'll just invoke convexity. This expression here in green, which is from the previous, I'm going to do summation. The summation over all values of t. Okay, so okay, somehow the 7 has come up here. It's actually 1, equation 1. I don't know why this is showing as 7, 1. So recall from the expression 1 that we had this gt transpose xt minus x star, exactly the expression here. I'm just I have this additional summation over t, so that's what I'll bring up now. Okay, so gt transpose xt minus x star summation now is upper bounded by two things, right? One is we'll have f of xt minus f of x star, and the other thing we'll be doing is this xt minus x star. We know that it's greater than 0. I mean, we have not yet reached the optimal solution. So as a homework, please try and complete this. I'm going to leave it at this point for today. Okay, so we have several elements in place. Complete the or rather the analysis on all the elements we have already brought together. Okay. Yeah, and we used telescopic summing, we used algebraic manipulation, we used convexity, we used Lipschitz continuity. Everything we have from our magic hat has been used. So now we should just take this to logical conclusion. Okay. Any questions before we conclude for today? Thanks everyone. See you on Monday to conclude this discussion.